Today, I want to cover the next 25 minutes or so on AI in enterprises. How are enterprises adopting AI? So if you look at it, there are three technologies that's really driving the enterprises today. One is AI, we all know. We all hear about AI. The second one is cloud. The third is quantum. So I'm also going to have IBM Research cover quantum with me on how AI is being implemented with quantum. But within AI, there are three trends that's developing. And those three trends are around data, algorithms, and the final one is around compute. So what do I mean by compute? The more data, the proliferation, the velocity, the veracity of data happens, you need more computing power. The traditional ways of computing doesn't work. So that's where quantum comes in. So we are going to cover that. Algorithms. As you develop and deploy these algorithms or models into enterprises, you want to make sure there's no bias there. It's fair. It's explainable. And the final one is data. So there's a perception that all data in enterprises exist in a CSV file, but it's not the case. Data is siloed. Data is fragmented. There's no way to get access to trusted data. I mean, I have worked with customers where they talk about self-service analytics, but it takes 6 to 8 weeks for a data scientist to get trusted data. What kind of a catalog for the metadata exists within their enterprises? How is that syncing between the existing catalogs, data catalogs that is out there? So the challenges with data in enterprises are real. So I want to invite, I had a pleasure of the last 2 days working with one of our customers from Green Bay, Associated Bank. So I also have the pleasure to invite him on stage to talk about some of the data challenges. That's Steve Lewick, who is the SVP, Senior Vice President and Director for Data Management. So thank you, Steve.
Thanks, Nash.
So, Steve, I mean, obviously you are a practitioner. I'm more of a preacher, so you're a practitioner. But we talk about data all the time. But even before we get to data, I mean, especially for the audience, what does AI mean to enterprise? I mean, there's a lot of talk about AI. Every enterprise wants to adopt AI. But what does AI mean to an enterprise?
Sure. From our perspective, obviously AI is unleashing new capabilities for our organization, unleashing new business insights from customer knowledge and insight all the way through to how our systems are functioning and operating. And really what we're trying to do is facilitate innovation across the organization. But I think when I look at it from an enterprise perspective and point of view, it's really about how do we scale and enable and empower the right users across our organization to be able to leverage and perform analytics across the data sets that we're now being able to provide, which is new data sets, new variables that never before could have been touched. We have some scenarios pop up recently around where areas of our industry or of our organization are not traditionally data scientists or even statistical modelers, but we're finding that by enabling the users around the bank, there's new opportunities where we had a model that was built for a research department within our team that they built completely independently in a silo, not on enterprise infrastructure. And we now are trying to provide a platform to them to enable those use cases, because we think that we're seeing a gray area between roles and responsibilities across the organization of who is actually performing analytics.
That's very important. I mean, I see myself that a traditional data engineer who used to wear that hat is now becoming a data scientist, and the same thing, because those are kind of like merging to some extent. But from a data perspective, like what challenges? I mean, I see the data silos and a lot of copies of data, a multitude of data existing, within enterprise. I mean, what challenges do you see with the data?
No, it's exactly that. We have data availability is still, like you mentioned in the opening, is still a big problem. And for us, and we want to try to provide a platform that's scalable and introduce consistency and governance and control across the enterprise, but still be fast and agile and nimble. One of the risks we have is that enterprise is often looked at as being slow, right? Anytime you talk enterprise, that's going to take too long. So we're looking at ways and frameworks and platforms to help us ingest that data rapidly, and have that governed and controlled all the way through the analytics, and enable the users through that.
Yeah, and one more point on Steve's. While we think enterprises are slow to adopt AI, there's a huge challenge in bringing AI into enterprises. It's not that easy and traditional because you're infusing AI into a technology that has existed for decades, third-party software, so many challenges exist. But finally, once you develop the model, you deploy the model, but then comes in an industry like yours or banking, there's so much regulatory oversight. How do you do it? How do you do explainability and other things that you need to do?
Sure, and again, that's one of the keys of the platform and the scale that we bring from an enterprise perspective is the explainability of the model is just as important as the model itself in a lot of cases from a regulatory and compliance perspective. So making sure that we understand and have the process in place to know where that data came from through the entire life cycle of that data, and we can explain that on the way out. There's a perception kind of in the space, especially in the banking and the legacy industry, is around the fact that that's a black box, right? When we introduce AI, we're going to lose visibility, we're going to lose that insight. We want to make sure that we have a platform that enables us to have that explainability so that we can dig right in and find out all the details.
Right. Two things I think Steve mentioned. One, platform. I think it's very critical for any enterprise that wants to embark on a journey of AI. It's very critical to have a platform. Because all the way from ingest to visualization, if you have a set of services that's already stitched together, that becomes a lot more easier than you bringing a governance service or a data ingestion service and a visualization service and trying to stitch it together. The next point that you mentioned, black box, I mean, that's also very true. So that takes me into my next small snippet of a video that I want to show you, but let me thank Steve first. Thank you, Steve, so much for coming on stage. I know you have to fly back, but thanks for coming back and sharing with us your experiences.
Thanks, Dinesh.
So here I want to show you, Steve talked about the black box, but when we talk about interaction with data, we have been interacting with data for a while, right? I mean, through your computers, obviously you have been interacting. But now it's changing to talk to your data. I mean, if you think about chatbots, you're talking to the data and the data is kind of talking back to you. Same thing with home assistants, right? I mean, you get some level of talking going back and forth. But at IBM, we have been, in my development lab, we have been doing some initial research on what if you walk with your data, or what if you walk into your data, meaning it becomes a lot more easier if you can visualize data in a 3D perspective or from a virtual reality perspective. So I want to show you like a minute video of what we have done where explainability becomes so much more easier when you can visualize from a 3D perspective. Take a look at it.
Our virtual reality environment allows you to step into your model like never before. Here we can see our machine learning model waiting to be explored. When we crack open the black box, we can immediately see all 25 features selected by the model. The ones closest to us have the largest contribution to the model's decisions. Those further away contribute the least. Features in an AI model don't operate in a vacuum. The interaction between features play a huge role in the working of the model. The more we can understand this interplay, the better we can make sense of our model. Let's select two features: unemployment rate and interest rate. This launches a 3D scatter plot. We can see how multiple features, added together, impact the model output. Analyzing a 3D scatter plot helps us see the data from different perspectives. Let's focus on the bottom cluster and view it from the perspective of interest rate. You might expect people to default on their loans when the interest rate rises, but that's not the case. The downward slope along the axis tells us as long as the unemployment rate remains low, rising interest rates actually make people less likely to default. The downward slope simply can't be seen in 2 dimensions. But in virtual reality, the insights begin jumping out. Using these immersive tools, we can explore our model in a more intuitive way, bringing us one step closer to cracking open the black box and understanding how our AI model is making predictions.
So you see how, I talked about walking with your data, walking into data, where you can really visualize from a 3D perspective. And especially in the industries like what Steve talked about, explainability becomes very critical, and this really helps. The second trend that we see is algorithms. So I called it algorithms because once you deploy the model, people think that that's it. You deployed the model. But that's where the real work starts, I think, in an enterprise. Because think about it. Once you deploy the model, you want to make sure the model is not drifting, obviously. The model is fair. The model is not biased. All those things is part of the algorithms. And in the next video clip, I want to show you where we worked with Wimbledon, and you will see that bias exists in the most unexpected places. And when you see the video, you will never see bias in there, but I'll point out to you. So take a look at the video, and then let me take you through it where bias exists.
Technology is changing the way we view sport. Wimbledon, through their partnership with IBM, is at the cutting edge of this technology. Thanks to groundbreaking AI systems using IBM Watson, the best highlights from multiple matches are captured simultaneously. With over 18 courts and up to 4 matches per court each day, hundreds of hours of footage are produced, which would ordinarily take a team of editors a huge amount of time to compile into highlights packages. As the AI highlights system continuously tracks the action and ranks every point, highlights packages are created within 2 minutes of a match finishing. By watching player reactions, listening to crowd excitement levels, and analyzing the gameplay statistics, IBM Watson enables Wimbledon to deliver unmissable moments without delay.
Can we go back? So let me run through the high-level, architecture of that, and then if you could take a guess where the bias existed. I mean, it's really hard, but what we did was that obviously there's tremendous amount of unstructured and structured data that comes in. We created the features, for example, player ranking, venues, crowd cheer, crowd noise level, all those things, and we built a model. And what we realized is that every time the model is picking the higher-ranked, well-known players for highlights. So think about it. It's always Federer, Nadal, Venus Williams, or maybe Venus is not top anymore, but Serena. So it always picks the top-ranked players. So once we run through the bias detection software of Watson OpenScale, we were able to bring up lesser-known players because if you think about it, the features that we were using were crowd cheer, venue. I mean, obviously the top-ranked players get the center court. They get larger crowd. Their crowd tend to be more louder. So the model continuously picked, the top-ranked players. But once we ran through the Watson OpenScale and bias detection, we were able to bring lesser-known players like Shintaro, who had really good games that day and some really nice shots. But we were able to bring them to the top. But not only that, it gives an opportunity for lesser-known players to be advertised or being brought to limelight. So it helps from 2 perspectives, right? So that's what we did with bias detection. And that's why I said, sometimes bias exists in the most unexpected places. Nobody would have thought, okay, all right, there's the Federer's highlight, but it would never happen in your mind that there is bias exist. And that's what, I call it subconscious bias or muted bias that is hard to, detect. So what does it take? What does it take for us to build a model that is, trustworthy, right? I think there's 4 pillars to it. 1 is explainable. How do you make sure that's explainable? So especially when you have a bank, for example, you want to make sure the model is explainable. If you give a loan, it's for sure the regulator will come and ask, why did you deny this loan? Fair. How do you make sure the model is fair and there's no bias in there? 3, accurate. I mean, you want to make sure you want to detect model drift even before it starts happening, right? So it's very critical. I have some concrete examples. So obviously, given the time, I cannot go into it. But model drift is real. As the data changes, model is going to drift. The last thing is open. I honestly, truly believe that this is the biggest undertaking. AI is the biggest undertaking of our lifetime. If we don't get this right, there's going to be large consequences. We got to make sure that these algorithms are not held by one vendor or one company or one enterprises, but it's out in the open. That a community is behind it to make sure that the models that we build, the training data sets we use, is not creating biased and unfair models. So it's very critical that we make it as open as possible. So if you take Watson OpenScale, for example, I mean, we do what we are preaching. We have contributed tremendous amount of technology into it. So if you take, for example, explainability, if you take for Fairness 360, Robustness Toolkit, all of them are available on Git. We have contributed back into the community, and we are more and more focused in making this open so that bias and fairness, doesn't exist, unfairness doesn't exist in the models going forward. The last piece is compute, and for that, I want to invite Abraham, who's an IBM researcher in the quantum side, and working with AI and quantum to see how do we, as the data proliferation happens, how do we make sure that we bring more computing power into it? So for that, where else can you turn than to qubits and quantum? So for that, let me invite Abraham to come and give you a high-level view on what we are doing from IBM Research. So Abraham, thank you.
Hello, everyone. Let's begin. So today I would like to talk to you a little bit about quantum computing and AI and how those two work together. So let's begin first with just this opening page. How many of you have seen this picture of a golden chandelier-looking thing in the past? See some hands? So the idea here is the quantum devices that at least IBM is working on are made out of superconductors. And so those superconductors have to be cooled down to low temperature in order to work with those devices. So we have something here that's called a dilution refrigerator. And you see several lines bringing in microwaves to your device, because microwaves are how you communicate with the device. At the end of the day, the chip sits at the very bottom, and we have qubits instead of classical bits to work with. So now the question becomes, how do we use these qubits, and how are they relevant to industry applications? And in this case, I'll show you a quick example of using quantum computing in the field of AI. So let's start very simply by introducing the field. So the history of the field goes as far back as the early days of quantum mechanics. So here I've put the earliest days as 1935, when people were trying to understand the implications of quantum mechanics as a field of physics. Very quickly, the field has come to a point where we're now focused on applications. So how do we extract application advantages out of quantum computers? So you can see as early as 1984, IBM has been working on this field and proposing algorithms for use in cryptography, for example. The field accelerates very quickly, and here we are. In 2016, IBM was the first company to put a quantum computer on the cloud, which means the field has gone from something that's in a research lab to something that's out in the open. So anyone can access a quantum computer now. And since that time, some exciting announcements have come. More recently, IBM announced a new data center in New York, and our largest quantum device yet with 53 qubits. Okay, so let's start with some basics. So what are we dealing with? So let's first talk about the computers that we have today versus quantum computers. So on the left, I've put 2 coins here with heads and tails to indicate that we have 2 options, so 0 and 1. And our computers today work with this level of information. Out of your transistors today, you can build AND gates, OR gates, NOT gates, and so on, and build logic based on those gates. So at the end of the day, your logic is computing on zeros and ones, flipping zeros to ones, ones to zeros, and vice versa. On the other hand, on the right side, I'm trying to show you a representation of the state of a qubit, which is a quantum bit. Here, instead of having just 2 states up and down, you have multiple states along the surface of that sphere in the picture. So really, you can have a qubit that's in any state along the surface of the sphere, and what this tells you is that the feature space that's available to you is fairly large. So this is one of the 2 principles that I would like to tell you about to take advantage of quantum computers in a real field like artificial intelligence. So this is one property, right? So the state of a qubit can be anywhere along the surface of this sphere. Another property that becomes important is, so that first one is called superposition. You might have heard about this. The second property that becomes important is that 2 qubits that come together can interact in such a way that once you have them apart, their properties are correlated. So if I flip 2 coins right now, the outcome of the two coins doesn't necessarily need to be correlated. But with quantum bits, that's not true. The outcomes can be correlated. And so what this does is give you a much larger feature space to play with. OK, so without going into too much detail, one point that I really want to get across today is that you can go to quantumcomputing.ibm.com, where you'll be met with a web page that looks like this, and you can write code on a quantum computer and execute it yourself. So you'll be met with a page that looks like this, where you can build a circuit graphically. So think of the old days of computing where you needed to build circuits with AND gates, OR gates, NOT gates. A similar concept, so you can use a graphical interface to build your circuits. Or you can write code that's very familiar to most of you here, I'm sure. You can write code in Python to then program a quantum computer and get measurement outcomes from that quantum computer. So how do those two screens look? Here's a screenshot of the circuit composer. Those 5 lines that you see here, horizontal lines, are individual qubits. And you can see I've dragged and dropped among that series of gates that are available a few select options on those qubits. So generally, this is how you'd build a quantum circuit by dragging and dropping using the circuit composer on that page. There's also an interface for you to write code. So this code looks very simple, right? I'm saying circuit.x, so apply an x gate on qubit 0, and you can see that very first x gate on qubit 0. So you can build your quantum circuits very simply writing programs in Python like this. OK, so now that you know that you can go ahead and build a quantum algorithm, whether it's graphically or in code, the question becomes, how do we do useful things? And in this case, I want to show you how easy it is to build a quantum SVM kernel classifier. So here, the challenge is going to be, I have a data set that looks something like this, and I'm going to try to come up with a way to classify that data into the several pieces of classification. So there are 2 challenges that come up here, right? The first question is, how do you represent data into the quantum computer for it to then do the number crunching for you? The second part that comes up with that you come across is, how do you then compute on the data once you've encoded it? So these details have all been written out for you in Qiskit. So Qiskit stands for Quantum Information Science Kit. This is an open source quantum computing software. And in Qiskit, there are many layers for you to get involved at the application level. So what I want to show you is how easy it is to build a quantum algorithm to do this kind of classification in Qiskit. So take a look at this piece of code. So this is all you need to get the code to classify that data. So what I'm doing is first saying the algorithm is a QSVM. So that's a quantum SVM kernel. I'm doing a feature map, which I've described here. So for the details of this feature map, we can talk offline. And I'm doing a multi-class extension. So because this is data with multiple classes instead of just 2 classes, I can extend traditional classification models using multi-class extension. And I'm saying I would like to do 1,000 repetitions of this experiment and see what a quantum computer says. And it's that simple. So you can build your quantum algorithm programmatically like this, just describing the pieces that you need. I want a quantum SVM kernel. This is how I'd like the information to be mapped, and I'd like to work with this algorithm. So we have, for the algorithm, the input is the training data, and we also test with the test data. And that's it. You take that bit of information that you built to describe the algorithm, and you just say, run it. And the quantum computer gives you the results from this. So if you run it, at least in this particular example, I'm able to classify this data with 80% accuracy. And as you'd traditionally expect, we can get the predictions out, we can get the results, and compare what our outcomes were with what we would expect to see. So one thing I would like to point out here is there was a paper published by IBM Research and coworkers in Nature earlier this year showing exactly this kind of concept. So supervised learning with quantum-enhanced feature spaces. So taking advantage of the large feature space that's available to you in quantum mechanics to do work in terms of classifying data. So I would strongly suggest that you take a look at this paper. And One point I'd like to leave you today with is that you can still go to this website, start programming your own quantum algorithms, start learning how this field can be leveraged in your application, and we have made several tools to make sure that you have an easy time doing this. So one of those is we've put out a Learn Quantum Computing Using Qiskit textbook. So the idea here is that you can go through a textbook that's open source and available online and start learning how to program these quantum computers. We also know that people like to learn from watching videos, so we also have videos available for you online. You can take advantage of these videos and learn how to install Qiskit on your computer and run code from it. And because this is open source software, you can also learn how to contribute to the open source project. Okay, thank you all. One final thing I'd like to say. So there's a session today at 1:30 where we'll go into a deep dive on the kind of code that you saw earlier. I'll show you how to build quantum circuits, how things work, and we'll build circuits together at that session. So 1:30 p.m. Deep dive. I'll call Dinesh back to the stage now. Thank you.
I'm good. Thank you, Abraham. I mean, you saw what we have done from a quantum compute perspective, from a data perspective, and from an algorithm perspective. So please, reach out if you have any questions. We have also a booth on 516. But thank you so much for your time. Appreciate that.